everybody. It's my pleasure here to give you a presentation, an overview of some of the things that we have been doing in Ghent University, where, of course, it typically fits within this meeting on hydrogen material interaction. And we have already seen a few examples of how nice experimental work, and like the previous talk, for example, how nice experimental work can help us to find some information about this interaction between hydrogen and materials. And basically, this is also the purpose of my talk. So how with dedicated experimental work, you can actually see some effects of hydrogen on your material. So about the hydrogen material interaction, well, to start with, I want to point out some particular features of this interaction, because I will focus on them during the experimental work and the data I'm going to present. So the first thing which makes hydrogen research very complex is the fact that hydrogen is a very mobile atom, especially, of course, in BCC structures. So there you have a very high mobility. So hydrogen moves while you are doing an experiment. But on the other hand, which is also a structure we can have in steel, so namely the face-centered cubic structure. For example, in a duplex stainless steel, you have both. But in an FCC structure, hydrogen is extremely slow. Here you see some indicative values on this hydrogen diffusion coefficient. Typically, it is in pure ferrite, and this is then in austenite. On the other hand, you have the solubility of hydrogen. This is quite low in a BCC structure, but on the other hand, quite high or very high sometimes in FCC structures. So this also has an effect on how you do your experiments if you want to go and to reach saturation. Now, very specific about the interaction between hydrogen and your microstructure is actually the difference between diffusion and trapping. Now, hydrogen can be mobile, but at some points in your microstructure, hydrogen can be trapped. This means that it stays there for a certain amount of time. Now, this trapping can be reversible, which means that hydrogen is easily escaping from the trap of, for example, when you are putting some additional higher temperature, it escapes very quickly, but it can also be irreversible, which means that at room temperature, once it's trapped, it stays over there, and it only starts moving when you put additional high amount of thermal energy in your material. So when you go like the temperatures to 500-600 degrees centigrade. And then another thing, it's very difficult to have a direct observation of hydrogen in your materials. Nowadays, you have some very nice examples of atom probe tomography who show you some spots where hydrogen can be, but this is a very delicate experimental technique on a very small sample. So it allows you to have some direct observation of hydrogen, but on a very limited amount of material. Now, all these features, actually, they imply that it's extremely important that when you do experiments, that you do this via a very specific experimental methodology. And I will show you some examples how with careful doing experimental work, you can elucidate some of the features related to hydrogen. Now, I will focus on a few things. I will focus on the fact that hydrogen affects mechanical properties and show you some examples of this. The fact that hydrogen is mobile, the fact that hydrogen can get trapped, and then I will also show you how material characterization techniques and advanced techniques can give you additional input on how hydrogen behaves inside your material. So first, let's start with the mechanical tests. When we do mechanical tests, we have, of course, different type of ways how to do a test. Previous speaker talked about bending. Well, we have here, and I present you here some results on in-situ tensile tests to quantify the effect of hydrogen embrittlement. Now you have this typical formula, which is a little bit hidden over here, where you see the amount of hydrogen embrittlement is actually the difference in the strain between a sample which is charged in air, being not in contact with hydrogen, and a sample that is saturated with hydrogen before doing the tensile test. Now, how do we do these tests? Well, this is a typical setup, but it's important here, what you see over here, we do in situ tensile testing. This means that we have actually an electrochemical cell built around our specimen, and we can charge our specimen or before doing the test, and then we work on saturated samples, or while we start the test. And then we will see, and I will show you an example of that later on, that actually hydrogen moves inside your material while you are performing a test. Here you see a few results. And well, first you see here tests in air, A and B. This is actually 2 times the same test we perform. And you clearly see the reproducibility of the test here, because both curves are nicely on top of each other. And then you have here what is called charged A and B. And this is that we saturate our sample with hydrogen. So typically for a tensile specimen, we charge it for 1 or 2 hours when it's 1 millimeter thick in order to be sure that we have saturation. And then you can clearly see that we lose some of our ductility during the test when we charge it with hydrogen. So clearly the ductility has dropped significantly in this material due to the detrimental effect of hydrogen. Now the curve I just showed you is this one over here. It's for trip steel, so transformation-induced plasticity steel. And as just indicated, you see here a clear effect of hydrogen on your ductility. Now, this test allows us to compare materials very quickly. Previous talk mentioned, for example, HSLA steels, high-strength alloy steels. Well, these steels, there the effect of hydrogen is quite limited because these steels have the titanium and niobium carbides present there. So you see a clear difference between the trip steel, which is typically an automotive steel, and the HSLA steel. Now, sometimes when you have the standards, then people say, like the sensitivity of a material to hydrogen is related to its strength. Well, here you see 2 materials which have actually pretty much the same strength level. So there's a clear difference in how hydrogen affects the ductility in these materials. So just saying that a high strength material is more sensitive to hydrogen than a lower strength material is not correct. And we have also to take into account that because there is no direct correlation between strength level and hydrogen sensitivity, that actually is the microstructure of your material, which is essential. So this is why it's also important that you try to combine experimental work with this material characterization techniques. Here, when we compare those 2 materials, typically, the role of carbides there is very important. And I will come back to the role of carbides later on in my talk. So first, let me say something about hydrogen diffusion and the role of hydrogen diffusion during a mechanical test. So here there's a lot of information on this slide. And actually here we did several tests on a DP steel, a dual phase steel, industrial material containing ferrite and martensite. And in this steel, so actually we did tests in air and we did tests on samples which were non-pre-charged. This actually means that you can see here, the non-pre-charged. This actually means that you have your specimen and you start the charging from the moment you start pulling your specimen. So this means that hydrogen can start entering your material when you are doing the mechanical test, but it can also only diffuse in certain extent inside your material. And the idea was, when we are, like you see over here, doing the tests at different cross-head deformation speeds, that actually we can vary the distance that hydrogen can travel inside your material during the test. And the idea was, can we see this effect of hydrogen on our sample when we do fructography on the specimens, and can we then see or correlate the distance that hydrogen has traveled with changes in fructography. So therefore, we calculated here the diffusion distance of hydrogen via the formula which is here mentioned. So here you need the diffusion coefficient, which we obtain via a permeation test, and then you have the time. Now, the time is the duration of the test, and if you pull your material faster, then of course the duration of the test will be slower. So we calculated the diffusion distances. You see the values over here. So when we do at a cross-set deformation speed of 5 millimeters per minute, so quite quickly, you see that the diffusion distance is only 65 micrometer. Of course, it's starting from both sides of your specimen. When we go 10 times slower, it was about 170 micrometers. And we go again 10 times more slow, then you have a distance of about more than 400 micrometers. So then you have the tensile tests. So you see when we do the tests in air for the different deformation rates, that actually the curves are nicely on top of each other. So you don't see a real effect there of the speed of deformation. But when we do the hydrogen charging, then you see a clear effect. So first, when we do the test at the fastest rate, so then you see that we have a ductility loss of about 20%. And then when we look at the fructography, you see actually a change in the morphology of your fructography with the distance. So here you have over a distance of about 60 to 70 micrometers, clearly a fracture surface which has been affected by the presence of hydrogen. So this zone here, something changed in how it breaks due to the fact that hydrogen is present over there. And then we did the test 10 times slower, and you can clearly see that there's an increased effect of hydrogen on the ductility. So we lose here 55% of our strain when it's hydrogen charged. And then you see also in the fructography a clear difference over here, because here you see that we have actually, again, a fracture surface with a distance related to the diffusion distance, which has been affected by hydrogen. When we go to the slowest strain rate, so then you have an effect of 70% of ductility loss. And then you can see here in our fracture surface that actually it's completely affected by hydrogen. Now the samples were less than 1 millimeter thick. So actually when you have 400 micrometers or more than 400 micrometers from both sides, actually you can see that hydrogen reached the center of your specimen. And certainly in the center of the specimen, we saw also the effect of the segregation by manganese sulfides. So here you see clearly how hydrogen is mobile during the test and how this actually affects the fructography. Now, we also do interrupted tensile tests because they can give us valuable information. This means that we do a tensile test, but we don't go up to fracture. We stop somewhere in between at a certain point for a certain reason. And the idea there is that this should give us some information on the effect of hydrogen on a particular feature in our microstructure. So, for example, something that we were interested in was the effect of hydrogen on the stacking fold energy. Well, you know that in an FCC material, in an austenitic material, that actually when you are deforming it, several things can happen. And these several things are related to the stacking fold energy. So you can have deformation via dislocations, but certainly in the less stable austenites, you can also have an effect of formation of alpha prime martensite or epsilon martensite. And this is related to the stacking fold energy. Now, in literature, there are findings where people say that hydrogen is an effect on the stacking fold energy, but it's not so straightforward to exactly determine this effect. And therefore, we did some tests on duplex stainless steel, so where you have ferrite and austenite present. And here you see, again, the tensile tests up to fracture. So you see here that when we do the tests in air, you have a certain strain. And then when we charge the material for 24 hours with hydrogen, so take into account it's duplex steel. So this means that you have certainly in the austenite a very low diffusion rate. So also a very long time needed to go to saturation. So here we charge it for 24 hours. And you see that this is a clear effect on the ductility. So you lose some of your ductility. Now, our idea was to do interrupted tests at the strain level, which was reached in both conditions. So we do interrupted tests here at about 26% engineering strain, and at this fixed strain level, we have actually wanted to compare how the microstructure looked like for both conditions. So these are interrupted tensile tests where we stop at the same point and we say, okay, if we compare those two conditions, then we clearly see the effect of hydrogen on how your material deforms. So first, for our duplex stainless steel, we have the interrupted test in air, and then we took the specimen, and then we went to the scanning electron microscope in order to do EBSD measurements, so electron backscatter diffraction measurements. And this is the result of this EBSD analysis. So here you see, well, here these are the image quality maps, which gives you an idea about the band contrast, so how good the diffraction pattern is. And then here you have a phase map. And a phase map, actually there you have a colorful picture, and the color corresponds to the phase in the structure. So here in the initial material, it's a duplex stainless steel. So this means that you have here a structure where you have some ferrite and you have some austenite. Austenite is in red. Now, the third phase where we were looking for is epsilon martensite, because this is a phase which you can form when you deform austenite, and this can give rise at that moment to the formation of epsilon martensite. So this is a yellow color. Now, if you look at the specimen, initial specimen, well, you don't see any yellow color, so there's no epsilon martensite. When you look at the specimen of the air test after well, the interrupted air test, so 26% of strain, then when you look at this figure, well, you see that the dislocation density increased. Now, how do you see this? Well, this you see from the top picture, because your image quality map has, I would say, decreased in quality. And if you have more dislocations in your structure, then you have more disturbance of your diffraction pattern. And at that moment, you have actually less band contrast, so you have a darker image. And you can clearly see this. Now, if you would compare those two pictures, you might say, okay, I see here a lot more austenite as compared to this one, because there's more red phase over here. But this is just by coincidence, because the material is a banded material where you have zones with more austenite and zones with less austenite. So actually, the fact that this is a more red-colored picture is actually by coincidence. And then we go to do the same test with the same amount of deformation, but before doing the test, we charged for 24 hours our material with hydrogen. So we have the same strain level in the material, but additionally here we have an effect of hydrogen. And the idea was now, if we compare the microstructure with EBSD and we see differences, then we can attribute these differences to the effect of hydrogen in your structure. And this is how it looked like. So here you see the same two pictures here on the left, so the image quality and the phase map for the initial and the air interrupted. Then you have here the 24 hours hydrogen charged interrupted tensile test. And then you can clearly see in the red zones that the yellow color appears there very clearly. So you see here that there is clearly, apart from the fact that, okay, the band contrast again decreased and dislocation density increased on the materials, but you see very clearly here in the austenite that some epsilon martensite is formed. And you might even see here, when you look carefully, that inside these epsilon martensite LEDs, you see small green islands popping up. And those small green islands are actually alpha prime martensite, which is actually a second step in your deformation process. So you can have first austenite, this goes to epsilon martensite, and then in the next step you can form alpha prime martensite. So when we are looking at these pictures, we can conclude that, okay, again, the dislocation density increased, but we have also the presence here of epsilon martensite and alpha prime martensite. Now, when you look in the deformation modes in austenite in the relation to the stacking fold energy, well, then you can conclude actually that the stacking fold energy in the austenite is decreasing by the effect and by the presence of hydrogen. So you can clearly see that hydrogen affects here how your material behaves when you deform it, and it actually has activated an alternative deformation mode via the formation of this epsilon and alpha martensite. Now, maybe here you say, okay, this is not so clear, so this is why we went into more detail on a zone like this, and we zoomed in. And here you see this picture with more details, so with a smaller step size, so a smaller area was scanned. And then you see here inside this grain, and here you see the different orientations in this inverse pole figure map, and here you see the phase map. So you see here in this grain, clearly the three phases present on a distance of a few micrometers. So here you see 4 micrometers. So on a micro scale, you have here different crystallographic structures, which is related to the effect of hydrogen. So here you see the yellow zones again, which are the epsilon martensite, and you have here the alpha prime martensite. So in the single epsilon martensite LEDs, and then you have this alpha prime martensite, which is formed inside the epsilon LEDs. So we think that by doing these interrupted tensile tests, that you can clearly see that hydrogen has an effect on the stacking fold energy of your material. Now, I already stressed a few times that hydrogen is mobile, so that hydrogen diffuses at a measurable rate at room temperature in the BCC structure. And for this purpose, we do then hydrogen permeation tests. Now, these are the classical tests based on the Davanathan-Stachursky method. So I will briefly explain this method to you, for those of you who are not familiar with it. So actually what you have a double electrochemical cell. And here you have your steel specimen. So this is actually the material, and from this material, you want to determine the hydrogen diffusion coefficient. So you have actually the left cell, which is the cathodic cell, and here at the surface, this reaction is taking place. So you see the electrons flow, and this actually forms at that moment adsorbed hydrogen. So as a result of this chemical reaction, hydrogen is here adsorbing at your metal surface, and then it can, at that moment, enter your material. And then it becomes absorbed hydrogen, it's inside your material, and then actually it starts to find its way through your material, so it starts diffusing towards the other side, because there's a gradient in your material, so this is the driving force. Here at your surface, you have this higher hydrogen concentration, and then this decreases, so you build up actually this permeation transient. Now, at that moment, at a certain moment, hydrogen reaches here, the other side of your specimen. So at that moment, it comes actually in the second electrochemical cell, which is the anodic cell. So there's an oxidation reaction is taking place. And then you have here this reaction which takes place. Now, at that moment, you have actually here this current and the electrons which flow over here. And this current is actually measured, and this buildup of this current will give us a value for the diffusion coefficient. You should also note that in order to avoid alternative chemical reactions, that we bubble the cells with nitrogen gas in order to remove the dissolved oxygen from our electrolyte. So this is a permeation test which we perform and which helps us to study the hydrogen diffusion coefficient. Now, here I show you some results of this technique, and actually we tested here different conditions for the same material. So I already mentioned in the beginning of my talk that the presence of carbides is very typical and very, I would say, beneficial, potentially beneficial for hydrogen embrittlement. So we did a lot of tests on carbide-containing materials. And actually, these are ternary alloys. These are actually simplified chemical compositions where we have 3 elements present, being, of course, the iron matrix in our steel, but then we add titanium and carbon in stoichiometric quantities in order to ensure that when we do the correct heat treatment, that we form titanium carbides in our structure. So we have the material, we go to quite high temperature in order to dissolve all the carbon and the titanium, and then we have an S-quenched structure. So if you do the permeation test, you see here that this S-quenched structure has the highest diffusivity. So hydrogen is, the easiest way for hydrogen to get through the material is in the S-quenched structure. Now, then after the quenching, we do some tempering. And tempering allows the titanium carbides to form. So when you do tempering for 1 hour, you have a lot of very small titanium carbides, which are distributed all over your matrix. And all these titanium carbides, well, they are affecting the hydrogen diffusion a lot. So they slow down the hydrogen diffusion, and you clearly see this in your permeation tests, because here, it's this curve over here, you see clearly that the diffusion is a lot slower. And this is because these small titanium carbides, they are distributed all over the specimen, all over your sample, and actually they hinder the motion of the hydrogen, because hydrogen comes in the neighborhood of the small titanium carbides. It can get trapped over there, reversibly or irreversibly, but in the end, this slows down the diffusion process. Now, when you do the tempering for 2 hours, at that moment, actually the carbides grow. So the amount of carbides in your material remains the same, but the carbides become larger, which means that they are again in your matrix, but they are less effective in slowing down the hydrogen, because hydrogen can more easily find its way through the microstructure, through the structure with the titanium carbides. And this here, you see this effect on the diffusion coefficient, because the diffusion goes again faster, because the titanium carbides, when they are larger, they become less efficient in trapping the hydrogen, and as such, they slow down the diffusion in a less efficient way. So with additional tempering, you are actually moving from a diffusion coefficient towards, again, the S-quenched structure. Now, in a minute, I will show you some thermal desorption spectroscopy data performed on these materials in order to demonstrate this trapping effect of the titanium carbide and how it evolves with tempering. But before that, I want to first give you some other results of the hydrogen permeation test. Namely, we do the same test, but we put stresses on your material. It was already mentioned this morning that stresses are important. Well, we actually put a constant load on our specimen. So we put it in a constant load setup, and then we try to understand what the effect is of hydrogen, of the elastic or plastic load on the hydrogen diffusion coefficient. So here you see some of the results. So these tests were done on a dual phase steel, so the ferrite martensite steel I mentioned before in my talk. And here you see the diffusion coefficient as a function of the stress on your material. So you have here the 0% of the yield strength, which means it's an unstressed specimen. And then we put certain amounts of stress on the material, 60%, 80% of the yield strength, and here we go up to yield strength. So you see here that when we increase the elastic stresses, that at that moment diffusion goes faster. Well, at that moment, actually, the hypothesis is that at that moment, because you are stretching your crystal lattice, and actually this is the only thing which changes in your material, that because of stretching the crystal lattice, hydrogen can more easily go through the material, can more easily jump from one interstitial position to the other. And at that moment, you have also an increase in diffusion coefficient. Now here you see 100% of the yield strength, but you have to take into account that this yield strength is actually 0.2% of plastic deformation. So at that moment, you already see an effect of plastic deformation of your specimen. And here you see that plastic deformation decreases, again, this diffusion coefficient. So at that moment, we were interested to see when we put higher stresses on our materials, so go beyond the yield strength, can we have then a further decrease of this diffusion coefficient? So here you have again 0% of the yield strength. We have seen that when we go to 100% of the yield strength, so this was on the previous slide, 100% of the yield strength is pretty much the same as 0%. So when we go further and we go to 120% of the yield strength, we see a small decrease of our diffusion coefficient. When we go to 140%, you see a more significant decrease. And the reason here is that in this material, due to plastic deformation, you have dislocations. And these dislocations, they are known to interact with hydrogen, and they actually slow down again the diffusion process because hydrogen gets hindered in its mobility due to the presence of the dislocations. So you have actually two effects in your material: elastic strain, which opens up the lattice, and plastic deformation, where you have dislocations, and there the dislocations, they are actually slowing down. So then we say, okay, let's try to separate both mechanisms. And this is what you see, or will see on this slide. So we have here the specimen of 120% of the yield strength, as I just showed. This is a constant load. This means that at that moment, you put this constant load of 120% of the yield strength on your specimen. This is a combination of elastic and plastic deformation. So we have here this 1.2 star of 120% star of the yield strength. And actually the idea was that we release the elastic stresses of our material, and then we purely see the effect of the dislocations. So you see over here, 0%, then here 120%, where you have two effects combined. One effect is the fact that the elastic stresses are still present, still stretching up the lattice, opening it up so hydrogen diffusion can increase, but the presence of dislocations there decreases it. And here you have the elastic stresses removed, so it's purely the effect of the presence of dislocations, and then you can see this larger decrease in the diffusion coefficient because at that moment you have actually only the retarding effect of the dislocations on your diffusion coefficient. So as such, with this test, you can clearly see the effect of stresses on the plastic, on the diffusion coefficient, and that there's a difference whether you are in elastic mode or in plastic mode. Now, a few minutes ago, I showed you the effect of carbides, and I referred to thermal desorption spectroscopy data. So here we actually tested those materials with thermal desorption spectroscopy. So we have these materials. So this is the S-quenched iron carbon titanium alloy. And then we are saturating our material. So we charge it electrochemically with hydrogen in order to be sure that it's saturated. And we do the TDS. And then you see here in thermal desorption analysis, you see a certain peak. Now, this is hydrogen in your martensitic structure, which is then reversibly trapped at the lead boundaries. And when we increase temperature here at 100 degrees centigrade, it comes away from the lead boundaries and it goes out of your specimen. Then here, this is the quenched and tempered structure. And this quenched and tempered structure, you see additional peaks popping up. You see here different peaks, additional peaks, and these peaks, after 1 hour of tempering, these peaks are there because titanium carbides, they can trap hydrogen. And this is what we also have seen in the permeation test on the diffusion coefficient, that these additional peaks and the effect that titanium carbide can trap the hydrogen are actually responsible for, on the one hand, slower diffusion, on the other hand, more peaks in our TDA spectrum. So this was after 1 hour of tempering. So can we confirm the hydrogen permeation data when we are also taking a look at the data for 2 hours? Well, therefore, we went to the transmission electron microscope, and here we made a size distribution of the titanium carbides. So in this structure, you see that you have a lot of small carbides after 1 hour of tempering. There were also some large carbides, which apparently were not dissolved when we did the annealing treatment. But these large carbides, they are so incoherent that actually they don't trap any hydrogen anymore. And you will see that the larger carbides don't trap any hydrogen anymore in a minute. So this was after 1 hour of tempering. I just showed you here in this figure. So this is here after 2 hours of tempering. After 2 hours of tempering, you see that, again, there are still some small carbides left, but the carbides increased in size. So you see more carbides, larger carbides. And when we go and take a look at the TDS spectra, Well, there you see that the peaks related to titanium carbides, they decreased. And this is because the total interfacial area has decreased. So it's less effective in trapping the hydrogen, and also it's less effective in slowing down the diffusion coefficient. The fourth peak here was even completely gone. So we did additional tempering treatments on these specimens. So we went up to 10 hours, and for 10 hours, all the small carbides were gone. We also only have some larger carbides. When we look at the TDS spectrum, we see here an even smaller peak. And we went even up to 20 hours of tempering. So then all the carbides are larger than 70 nanometers. And when we do the TDS spectrum, actually the spectrum was identical to the spectrum of the S-quenched structure. So apparently the titanium carbides in the configuration that we are investigating here, so for this material, those titanium carbides, they lose their trapping ability, their trapping capacity, when they are about 70 nanometer in size. Now we have done similar tests on different carbides, other carbides. I cannot show all of them here, but we have done tests on chromium carbides, molybdenum carbides, and all these, also vanadium carbides, and all these tests actually confirm that there is a certain size for each carbide when they lose their trapping capacity. I don't know all these sizes by heart, and it's not 70 nanometers for all carbides, but for every carbide you have this threshold in the trapping capacity, trapping ability of the carbide for hydrogen. Now, an additional question is, can you activate actually different traps in your material related on how you do the charging? So we have material with the titanium carbides. I have focused the entire presentation here around the titanium carbides. And we compared actually gaseous charging versus electrochemical charging, also taking into account that this gaseous charging is performed at a higher temperature. So charging is there done at temperatures of 800 degrees centigrade. And then here you have electrochemical charging. This electrochemical charging is, of course, done at room temperature. So we have demonstrated that gaseous charging at high temperature activates other traps in our structure than electrochemical charging at room temperature. And this was also confirmed with thermal desorption spectroscopy. So here you see different specimens, and there you see actually a high temperature peak. And this high temperature peak is actually hydrogen from the gaseous charging. You see here the different charging temperatures we did. So I mentioned 800. This is then the largest peak. So it's here, the one with black stars. And then we also did some lower temperatures, and we compared this to a cold-rolled structure. And you see that the titanium carbides, that they are able to trap more hydrogen when the titanium carbide size increases. So here you have a high temperature irreversible trap, which is activated by this gaseous charging at high temperature. Now, when we have these materials, and on these materials, we do additional electrochemical charging. The idea was, can we then at that moment activate the trap, which was responsible for the low temperature peak we have just seen in previous TDS spectra. And this is what you see over here. So these specimens were first charged in gaseous environment. So this is an irreversible trap, which means that the hydrogen stays there inside, and you can leave the specimen unattended for a long time. The peak there will remain. So you can leave even the specimen for a few weeks over there. The hydrogen will remain inside this high or this irreversible trap, or this high temperature peak related trap. And then this is the electrochemical charging. So this low temperature peak here was clearly demonstrated. So this is actually also the trap, which is to a certain extent, as shown before, related to the titanium carbides. And then we say, okay, let's wait for a certain amount of time to see whether the hydrogen can get out of our specimen when we do the test, and to see whether it's how mobile or how reversible the trap is. So here you see after 1 hour, you have this peak. When we wait 4 hours before we do the TDS spectrum, you see that the peak decreased. After 16 hours, again, a small decrease. After 64 hours, again, a small increase. Now, at that moment, you might say, okay, this is a trap related to titanium carbides. And this is a trap related to titanium carbides. Now, what's the difference between the two of that? Well, actually, when we saw these results, we were also quite puzzled, because how can you activate additional traps inside your material? Like is shown here with this high temperature peak. And actually, the answer to that question came from people who do DFT calculations. So they have this density functional theory calculations where they work with quantum mechanical calculations, ab initio calculations. And they actually showed with their calculations, and this actually nicely confirmed our results, that when we do the high temperature gaseous charging, because of the high temperature, you have more additional vacancies in your titanium carbides. So you have additional carbon vacancies because of the high temperature, and these carbon vacancies at high temperature, they get filled with hydrogen. And this is actually the peak we see over here. So because of the high temperature, hydrogen is able to enter the titanium carbide, and inside this titanium carbide, all the vacancies which are available there, or increased amount of vacancies available there, because of the high temperature, they get filled up with hydrogen. And once the hydrogen is there, it stays over there until you increase the temperature up to 600 degrees centigrade. While here, this low temperature peak is actually hydrogen, which is trapped at the interface. So the interface between the matrix and the titanium carbide. And this is what we very nicely see over here. And this is another trap, but again related to the titanium carbides. So here, irreversible traps where hydrogen is trapped inside your titanium carbide. And here, reversible traps where hydrogen is trapped at the interface of the titanium carbide with the matrix. And this also confirms that with increased tempering, you change your interface and the amount of interface. So this is why with increased tempering, we saw here also a decrease in the peaks. And then to end my presentation, I want to show you something related to advanced material characteristics and how these characterization techniques can help us tell us something about the behavior of hydrogen. So often people say, like, how sensitive is a microstructure to hydrogen-induced cracking? And people sometimes think that, okay, you can quote this in one number, or just say, okay, this material is very sensitive, but actually this happens on a microstructural scale. And all the details in your microstructure are extremely important and can have an effect or can behave differently when they're coming into contact with hydrogen. So what do we see over here? Well, this is the TRIP steel, transformation-induced plasticity steel. I showed some tensile tests off in the beginning of the presentation. And here in this TRIP steel, well, you know that this is a steel with multiple microstructural features. So you have in this steel, for example, islands of martensite and retained austenite. Martensite is known to be very brittle. Well, actually here, you have this small crack inside the martensite island. And this is actually a brittle failure of this small martensite island. So here, this island, which is 1-2 micrometer in length here, is failed in a brittle way due to the effect of the presence of hydrogen. But then this crack comes into the ferrite, and ferrite is more ductile. So at that moment, you see plastic deformation. You see a blunting also of your crack tip, which actually slows down the crack propagation rate. So here the ferrite is a ductile material, and you see that it's a different way how the crack behaves and how your material behaves. So how sensitive is a microstructure? Well, this depends whether you are talking to the retained austenite martensite islands, which are very sensitive, or the ferrite, which has the capacity to slow down the crack propagation. In this strip steel, we did a very extensive study, and we were able to see that in 85% of the cracks that we investigated, that 85% of these cracks were identified to be initiated in the martensite. The others weren't, but of course it's a 2D measurement, so it might be in third dimension, that just below the surface there's a martensite island which we don't see. But in 85% of the cases, it was clear that it started inside the martensite. And actually here, this is a mechanism which is based on the HEDI mechanism. In one of the previous talks, it was mentioned that you have different mechanisms like hydrogen-enhanced decohesion and hydrogen-enhanced localized plasticity. But actually you see here two mechanisms, both of them active on a distance of a few micrometers. Here you have a hydrogen-enhanced decohesion at the interfaces of your martensite lead boundaries. So this is why we call this a hydrogen-enhanced interface decohesion, which is happening in the martensite-austenite regions. And then you have the help mechanism, so hydrogen-enhanced localized plasticity, which is here happening in the ferrite. So how sensitive is a microstructure? Well, it depends on your microstructural features. And this is another figure where we were studying hydrogen blisters. Now, here you see a phase map, and this is actually pure ferrite. This is, of course, the crack inside. And then here you see some titanium carbides, quite large titanium carbides. Well, of course, crack initiation is always difficult to find because, what's the real initiation? But if you look here at the crack morphology, it's clear that initiation, most probably of the blister, which then opened up to the surface, that initiation of this blister was probably related to the titanium carbides. So this is also a nice example how these EBSD measurements, how characterization techniques can tell us something about the effect of hydrogen. And with this, I think I end up my time. I thank you for your attention.